The traveling salesman problem asks the following question: given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? It is an NP-hard problem in combinatorial optimization, important in operations research and theoretical computer science. Tsp is a special case of the traveling purchaser problem. In the theory of computational complexity, the decision version of the Tsp belongs to the class of NP-complete problems. Thus, it is possible that the worst-case running time for any algorithm for the Tsp increases suprapolynomially with the number of cities. The problem was first formulated in 1930 and is one of the most intensively studied problems in optimization. It is used as a benchmark for many optimization methods. Even though the problem is computationally difficult, a large number of heuristics and exact methods are known, so that some instances with tens of thousands of cities can be solved completely and even problems with millions of cities can be approximated within a small fraction of 1%. The Tsp has several applications even in its purest formulation, such as planning, logistics, and the manufacture of microchips. Slightly modified, it appears as a sub-problem in many areas, such as DNA sequencing. In these applications, the concept city represents, for example, customers, soldering points, or DNA fragments, and the concept distance represents traveling times or cost, or a similarity measure between DNA fragments. In many applications, additional constraints such as limited resources or time windows may be imposed. History: the origins of the traveling salesman problem are unclear. A handbook for traveling salesmen from 1832 mentions the problem and includes example tours through Germany and Switzerland, but contains no mathematical treatment. The traveling salesman problem was mathematically formulated in the 1800s by the Irish mathematician W. Hamilton and by the British mathematician Thomas Kirkman. Hamilton a unregistered trademark Ecosian game was a recreational puzzle based on finding a Hamiltonian cycle. The general form of the Tsp appears to have been first studied by mathematicians during the 1930s in Vienna and at Harvard, notably by Carl Menger, who defines the problem, considers the obvious brute force algorithm, and observes the non-optimality of the nearest neighbor heuristic. We denote by messenger problem the task to find, for finitely many points whose pairwise distances are known, the shortest route connecting the points. Of course, this problem is solvable by finitely many trials. Rules which would push the number of trials below the number of permutations of the given points are not known. The rule that one first should go from the starting point to the closest point, then to the point closest to this, etc., in general does not yield the shortest route. Hassler-Whitney at Princeton University introduced the name traveling salesman problem soon after. In the 1950s and 1960s, the problem became increasingly popular in scientific circles in Europe and the USA. Notable contributions were made by George Dantzig, Delbert Ray Fulkerson and Selma M. Johnson at the Rand Corporation in Santa Monica, who expressed the problem as an integer linear program and developed the cutting plane method for its solution. With these new methods they solved an instance with 49 cities to optimality by constructing a tour and proving that no other tour could be shorter. In the following decades, the problem was studied by many researchers from mathematics, computer science, chemistry, physics, and other sciences. Richard M. Karp showed in 1972 that the Hamiltonian cycle problem was NP-complete, which implies the NP hardness of Tsp. This supplied a mathematical explanation for the apparent computational difficulty of finding optimal tours. Great progress was made in the late 1970s and 1980, when Paragrafchal, Padberg, Rinaldi and others managed to exactly solve instances with up to 2392 cities, using cutting planes and branch and bound. In the 1990s, Applegate, Bixby, CHV et al., and Cook developed the program Concord that has been used in many recent record solutions. Gerard Reinault published the TSP-LIB in 1991, a collection of benchmark instances of varying difficulty, which has been used by many research groups for comparing results. In 2006, Cook and others computed an optimal tour through an 85,900 city instance given by a microchip layout problem, currently the largest solved TSP-LIB instance. For many other instances with millions of cities, solutions can be found that are guaranteed to be within 2 to 3% of an optimal tour. Description: as a graph problem, Tsp can be modeled as an undirected weighted graph, such that cities are the graph's vertices, paths are the graph's edges, and a path's distance is the edge's length. It is a minimization problem starting and finishing at a specified vertex after having visited each other vertex exactly once. Often, the model is a complete graph. If no path exists between two cities, adding an arbitrarily long edge will complete the graph without affecting the optimal tour. Asymmetric and symmetric: in the symmetric Tsp, the distance between two cities is the same in each opposite direction, forming an undirected graph. This symmetry halves the number of possible solutions. In the asymmetric Tsp, paths may not exist in both directions or the distances might be different, forming a directed graph. Traffic collisions, one-way streets, and airfares for cities with different departure and arrival fees are examples of how the symmetry could break down. Related problems: an equivalent formulation in terms of graph theory is, given a complete weighted graph, find a Hamiltonian cycle with the least weight. The requirement of returning to the starting city does not change the computational complexity of the problem. See Hamiltonian path problem. Another related problem is the bottleneck traveling salesman problem. Find a Hamiltonian cycle in a weighted graph with the minimal weight of the weightiest edge. The problem is of considerable practical importance, apart from evident transportation and logistics areas. A classic example is in printed circuit manufacturing, scheduling of a route of the drill machine to drill holes in a PCB. In robotic machining or drilling applications, the cities are parts to machine or holes to drill, and the cost of travel includes time for retooling the robot. The generalized traveling salesman problem deals with states that have cities, and the salesman has to visit exactly one city from each state. Also known as the traveling politician problem. One application is encountered in ordering a solution to the cutting stock problem in order to minimize knife changes. Another is concerned with drilling in semiconductor manufacturing. See for example, U.S. Patent 7054798. Surprisingly, Bezad and Modas demonstrated that the generalized traveling salesman problem can be transformed into a standard traveling salesman problem with the same number of cities, but a modified distance matrix. The sequential ordering problem deals with a problem of visiting a set of cities where precedence relations between the cities exist. The traveling purchaser problem deals with a purchaser who is charged with purchasing a set of products. He can purchase these products in several cities, but at different prices, and not all cities offer the same products. The objective is to find a route between a subset of the cities, which minimizes total cost and which enables the purchase of all required products. Integer linear programming formulation: Tsp can be formulated as an integer linear program. Label the cities with the numbers 0, n and define. For I equals 1, n, let b in artificial variables, and finally take to be the distance from city I to city j. Then Tsp can be written as the following integer linear programming problem. The first set of equalities requires that each city be arrived at from exactly one other city, and the second set of equalities requires that from each city there is a departure to exactly one other city. The last constraint enforces that there is only a single tour covering all cities, and not two or more disjointed tours that only collectively cover all cities. To prove this, it is shown below that every feasible solution contains only one closed sequence of cities, and that for every single tour covering all cities, there are values for the dummy variables that satisfy the constraints. To prove that every feasible solution contains only one closed sequence of cities, it suffices to show that every subtour in a feasible solution passes through city 0. For if we sum all the inequalities corresponding to for any subtour of k steps not passing through city 0, we obtain, which is a contradiction. It now must be shown that for every single tour covering all cities, there are values for the dummy variables that satisfy the constraints. Without loss of generality, define the tour as originating at city 0. Choose if city A is visited in step T. Then, since can be no greater than n and can be no less than 1. Hence the constraints are satisfied whenever for, we have. Satisfying the constraint. Computing a solution, the traditional lines of attack for the NP-hard problems are the following: devising algorithms for finding exact solutions. Devising suboptimal, or heuristic algorithms, that is, algorithms that deliver either seemingly or probably good solutions, but which could not be proved to be optimal. Finding special cases for the problem for which either better or exact heuristics are possible. Computational complexity, the problem has been shown to be NP-hard, and the decision problem version is NP-complete. The bottleneck traveling salesman problem is also NP-hard. The problem remains NP-hard even for the case when the cities are in the plane with Euclidean distances, as well as in a number of other restrictive cases. Removing the condition of visiting each city only once does not remove the NP-hardness, since it is easily seen that in the planar case there is an optimal tour that visits each city only once. Complexity of approximation, in the general case, finding a shortest traveling salesman tour is NPO complete. If the distance measure is a metric and symmetric, the problem becomes APX complete and Christofides Algorithm registered trademark S algorithm approximates it within 1.5. If the distances are restricted to 1 and 2, the approximation ratio becomes 8/7. In the asymmetric, metric case, only logarithmic performance guarantees are known. The best current algorithm achieves performance ratio 0.814 log n. It is an open question if a constant factor approximation exists. The corresponding maximization problem of finding the longest traveling salesman tour is approximable within 63/38. If the distance function is symmetric, the longest tour can be approximated within 4/3 by a deterministic algorithm and within by a randomized algorithm. Exact algorithms, the most direct solution would be to try all permutations and see which one is cheapest. The running time for this approach lies within a polynomial factor of the factorial of the number of cities, so this solution becomes impractical even for only 20 cities. One of the earliest applications of dynamic programming is the Helder-Euro-Karp algorithm that solves the problem in time. Improving these time bounds seems to be difficult. For example, it has not been determined whether an exact algorithm for Tsp that runs in time exists. Other approaches include various branch and bound algorithms, which can be used to process TSPs containing 40/60 cities. Progressive improvement algorithms which use techniques reminiscent of linear programming. Works well for up to 200 cities. Implementations of branch and bound and problem-specific cut generation. This is the method of choice for solving large instances. This approach holds the current record, solving an instance with 85,900 cities, see Applegate al., an exact solution for 15,112 German towns from TSP-LIB was found in 2001 using the cutting plane method proposed by George Dantzig, Ray Fulkerson, and Selma M. Johnson in 1954, based on linear programming. The computations were performed on a network of 110 processors located at Rice University and Princeton University. The total computation time was equivalent to 22.6 years on a single 500 MHz alpha processor. In May 2004, the traveling salesman problem of visiting all 24,978 towns in Sweden was solved. A tour of length approximately 72,500 kilometers was found and it was proven that no shorter tour exists. In March 2005, the traveling salesman problem of visiting all 33,810 points in a circuit board was solved using Concord Tsp solver. A tour of length 66,048,945 units was found and it was proven that no shorter tour exists. The computation took approximately 15.7 CPU years. In April 2006, an instance with 85,900 points was solved using Concord Tsp solver, taking over 136 CPU years. See Applegate al., Heuristic and Approximation Algorithms, Various Heuristics and Approximation Algorithms, which quickly yield good solutions, have been devised. Modern methods can find solutions for extremely large problems within a reasonable time, which are with a high probability just 2–3% away from the optimal solution. Several categories of heuristics are recognized. Constructive heuristics. The nearest neighbor algorithm lets the salesman choose the nearest unvisited city as his next move. This algorithm quickly yields an effectively short route. For n cities randomly distributed on a plane, the algorithm on average yields a path 25% longer than the shortest possible path. However, there exist many specially arranged city distributions which make the NN algorithm give the worst route. This is true for both asymmetric and symmetric TSPs. Rosenkranz al. 1977, showed that the NN algorithm has the approximation factor for instances satisfying the triangle inequality. A variation of NN algorithm, called nearest fragment operator, which connects a group of nearest unvisited cities, can find shorter route with successive iterations. The NF operator can also be applied on an initial solution obtained by NN algorithm for further improvement in an elitist model, where only better solutions are accepted. Constructions based on a minimum spanning tree have an approximation ratio of 2. The Christofides algorithm achieves a ratio of 1.5. The bitonic tour of a set of points is the minimum perimeter monotone polygon that has the points as its vertices. It can be computed efficiently by dynamic programming. Another constructive heuristic, match twice in stitch, performs two sequential matchings, where the second matching is executed after deleting all the edges of the first matching, to yield a set of cycles. The cycles are then stitched to produce the final tour. Iterative improvement, pairwise exchange. The pairwise exchange or two-opt technique involves iteratively removing two edges and replacing these with two different edges that reconnect the fragments created by edge removal into a new and shorter tour. This is a special case of the K-opt method. Note that the label Liene-Euro-Kernighan is an often heard misnomer for two-opt. Liene-Euro-Kernighan is actually the more general K-opt method. K-opt heuristic, or Liene-Euro-Kernighan heuristics, take a given tour and delete k mutually disjoint edges. Reassemble the remaining fragments into a tour, leaving no disjoint subtours. This in effect simplifies the teaspoon under consideration into a much simpler problem. Each fragment endpoint can be connected to 2Ka. Two other possibilities, of 2K total fragment endpoints available, the two endpoints of the fragment under consideration are disallowed. Such a constrained 2K city teaspoon can then be solved with brute force methods to find the least cost recombination of the original fragments. The K-opt technique is a special case of the V-opt or variable opt technique. The most popular of the K-opt methods are 3-opt, and these were introduced by Shen Lin of Bell Labs in 1965. There is a special case of 3-opt where the edges are not disjoint. In practice, it is often possible to achieve substantial improvement over 2-opt without the combinatorial cost of the general 3-opt by restricting the three changes to this special subset where two of the removed edges are adjacent. This so-called 2.5-opt typically falls roughly midway between 2-opt and 3-opt, both in terms of the quality of tours achieved and the time required to achieve those tours. V-opt heuristic, the variable opt method is related to, and a generalization of the K-opt method. Whereas the K-opt methods remove a fixed number of edges from the original tour, the variable opt methods do not fix the size of the edge set to remove. Instead they grow the set as the search process continues. The best-known method in this family is the Liene-Euro-Kernighan method. Shen Lin and Brian Kernighan first published their method in 1972, and it was the most reliable heuristic for solving traveling salesman problems for nearly 2 decades. More advanced variable opt methods were developed at Bell Labs in the late 1980s by David Johnson and his research team. These methods build on the Liene-Euro-Kernighan method, adding ideas from taboo search and evolutionary computing. The basic Liene-Euro-Kernighan technique gives results that are guaranteed to be at least 3-opt. The Liene-Euro-Kernighan-Euro-Johnson methods compute a Liene-Euro-Kernighan tour, and then perturb the tour by what has been described as a mutation that removes at least 4 edges and reconnecting the tour in a different way, then v-opting the new tour. The mutation is often enough to move the tour from the local minimum identified by linear Euro-Kernighan. V-opt methods are widely considered the most powerful heuristics for the problem, and are able to address special cases, such as the Hamilton cycle problem and other non-metric TSPs that other heuristics fail on. For many years Linear-Kernighan and Euro-Johnson had identified optimal solutions for all TSPs where an optimal solution was known and had identified the best known solutions for all other TSPs on which the method had been tried. Randomized improvement, optimized Markov chain algorithms which use local searching heuristic sub-algorithms can find a route extremely close to the optimal route for 700 to 800 cities. Tsp is a touchstone for many general heuristics devised for combinatorial optimization such as genetic algorithms, simulated annealing, taboo search, and colony optimization, river formation dynamics and the cross-entropy method. And colony optimization. Artificial intelligence researcher Marco Dorigo described in 1997 a method of heuristically generating good solutions to the Tsp using a simulation of an ant colony called ACS. It models behavior observed in real ants to find short paths between food sources and their nest, an emergent behavior resulting from each ant's preference to follow trail pheromones deposited by other ants. ACS sends out a large number of virtual ant agents to explore many possible routes on the map. Each ant probabilistically chooses the next city to visit based on a heuristic combining the distance to the city and the amount of virtual pheromone deposited on the edge to the city. The ants explore, depositing pheromone on each edge that they cross, until they have all completed a tour. At this point the ant which completed the shortest tour deposits virtual pheromone along its complete tour route. The amount of pheromone deposited is inversely proportional to the tour length. The shorter the tour, the more it deposits. Special cases, metric Tsp. In the metric Tsp, also known as delta Tsp or I-Tsp, the intercity distances satisfy the triangle inequality. A very natural restriction of the Tsp is to require that the distances between cities form a metric to satisfy the triangle inequality. That is, the direct connection from A to B is never farther than the route via intermediate C. The edge spans then build a metric on the set of vertices. When the cities are viewed as points in the plane, many natural distance functions are metrics, and so many natural instances of Tsp satisfy this constraint. The following are some examples of metric TSPs for various metrics. In the Euclidean Tsp, the distance between two cities is the Euclidean distance between the corresponding points. In the rectilinear Tsp, the distance between two cities is the sum of the differences of their x and y coordinates. This metric is often called the Manhattan distance or city block metric. In the maximum metric, the distance between 2 points is the maximum of the absolute values of differences of their x and y coordinates. The last two metrics appear for example in routing a machine that drills a given set of holes in a printed circuit board. The Manhattan metric corresponds to a machine that adjusts first one coordinate, and then the other, so the time to move to a new point is the sum of both movements. The maximum metric corresponds to a machine that adjusts both coordinates simultaneously, so the time to move to a new point is the slower of the two movements. In its definition, the Tsp does not allow cities to be visited twice, but many applications do not need this constraint. In such cases, a symmetric, non-metric instance can be reduced to a metric one. This replaces the original graph with a complete graph in which the intercity distance is replaced by the shortest path between A and B in the original graph. The span of the minimum spanning tree of the network G is a natural lower bound for the span of the optimal route, because deleting any edge of the optimal route yields a Hamiltonian path, which is a spanning tree in G. In the Tsp with triangle inequality case it is possible to prove upper bounds in terms of the minimum spanning tree and design an algorithm that has a provable upper bound on the span of the route. The first published example follows: construct a minimum spanning tree T for G, duplicate all edges of T. That is, wherever there is an edge from U to V, add a second edge from V to U. This gives us an Eulerian graph H, find an Eulerian circuit C in H. Clearly, its span is twice the span of the tree. Convert the Eulerian circuit C of H into a Hamiltonian cycle of G in the following way: walk along C, and each time you are about to come into an already visited vertex, skip it and try to go to the next one. It is easy to prove that the last step works. Moreover, thanks to the triangle inequality, each skipping at step 4 is in fact a shortcut. That is, the length of the cycle does not increase. Hence it gives us a teaspoon tour no more than twice as long as the optimal one. The Christofides algorithm follows a similar outline but combines the minimum spanning tree with a solution of another problem, minimum weight perfect matching. This gives a teaspoon tour which is at most 1.5 times the optimal. The Christofides algorithm was one of the first approximation algorithms, and was in part responsible for drawing attention to approximation algorithms as a practical approach to intractable problems. As a matter of fact, the term algorithm was not commonly extended to approximation algorithms until later. The Christofides algorithm was initially referred to as the Christofides Heuristic. Euclidean Tsp. The Euclidean teaspoon, or planar teaspoon, is the teaspoon with the distance being the ordinary Euclidean distance. The Euclidean teaspoon is a particular case of the metric teaspoon, since distances in a plane obey the triangle inequality. Like the general teaspoon, the Euclidean teaspoon is NP hard. With discretized metric, the problem is NP complete. However, in some respects it seems to be easier than the general metric teaspoon. For example, the minimum spanning tree of the graph associated with an instance of the Euclidean teaspoon is a Euclidean minimum spanning tree, and so can be computed in expected O time for n points. This enables the simple two-approximation algorithm for teaspoon with triangle inequality above to operate more quickly. In general, for any c greater than 0, where d is the number of dimensions in the Euclidean space, there is a polynomial time algorithm that finds a tour of length at most times the optimal for geometric instances of teaspoon in time. This is called a polynomial time approximation scheme. Sonia Barora and Joseph S. B. Mitchell were awarded the GAR Paragraph Dell Prize in 2010 for their concurrent discovery of a PTAS for the Euclidean teaspoon. In practice, heuristics with weaker guarantees continue to be used. Asymmetric teaspoon. In most cases, the distance between two nodes in the teaspoon network is the same in both directions. The case where the distance from A to B is not equal to the distance from B to A is called asymmetric teaspoon. A practical application of an asymmetric teaspoon is route optimization using street-level routing. Solving by conversion to symmetric teaspoon. Solving an asymmetric teaspoon graph can be somewhat complex. The following is a 3A, 3 matrix containing all possible path weights between the nodes A, B and C. One option is to turn an asymmetric matrix of size n into a symmetric matrix of size 2n. To double the size, each of the nodes in the graph is duplicated, creating a second ghost node. Using duplicate points with very low weights, such as AA, provides a cheap route linking back to the real node and allowing symmetric evaluation to continue. The original 3A, 3 matrix shown above is visible in the bottom left and the inverse of the original in the top right. Both copies of the matrix have had their diagonals replaced by the low-cost hop paths, represented by AA. The original 3A, 3 matrix would produce two Hamiltonian cycles, namely ABCA, score 9, and ACBA, score 12. Evaluating the 6A, 6 symmetric version of the same problem now produces many paths, including A or Euro squared B bar Euro squared C car Euro squared A bar Euro squared C or Euro squared A or Euro squared B car Euro squared A, all score 9 a Euro A. The important thing about each new sequence is that there will be an alternation between dashed and undashed nodes and that the link to jump between any related pair is effectively free. A version of the algorithm could use any weight for the A or Euro squared path, as long as that weight is lower than all other path weights present in the graph. As the path weight to jump must effectively be free, the value 0 could be used to represent this cost a Euro if 0 is not being used for another purpose already. In the two examples above, non-existent paths between nodes are shown as a blank square. Benchmarks. For benchmarking of teaspoon algorithms, TSP-LIB is a library of sample instances of the Tsp and related problems is maintained. See the TSP-LIB external reference. Many of them are lists of actual cities and layouts of actual printed circuits. Human performance on Tsp. The Tsp, in particular the Euclidean variant of the problem, has attracted the attention of researchers in cognitive psychology. It has been observed that humans are able to produce good quality solutions quickly. These results suggest that computer performance on the Tsp may be improved by understanding and emulating the methods used by humans for these problems, and have also led to new insights into the mechanisms of human thought. The first issue of the Journal of Problem Solving was devoted to the topic of human performance on Tsp, and a 2011 review listed dozens of papers on the subject. Tsp path length for random sets of points in a square. Suppose are independent random variables with uniform distribution in the square, and let be the shortest path length for this set of points, according to the usual Euclidean distance. It is known that, almost surely, where is a positive constant that is not known explicitly. Since, it follows from bounded convergence theorem that, hence lower and upper bounds on follow from bounds on. Upper bound, one has, and therefore, by using a naive path which visits monotonically the points inside each of slices of width in the square. Few proved, hence, later improved by Karloff. Lower bound, by observing that is greater than times the distance between and the closest point, one gets. A better lower bound is obtained by observing that is greater than times the sum of the distances between and the closest and second closest points, which gives. Hence, Held and Karp gave a polynomial time algorithm that provides numerical lower bounds for, and thus for which seem to be good up to more or less 1%. In particular, David S. Johnson obtained a lower bound by computer experiment, where 0.522 comes from the points near square boundary which have fewer neighbors, and Christine L. Valenzuela and Antonia J. Jones obtained the following other numerical lower bound. Analyst's traveling salesman problem. There is an analogous problem in geometric measure theory which asks the following: under what conditions may a subset E of Euclidean space be contained in a rectifiable curve? This problem is known as the analyst's traveling salesman problem or the geometric traveling salesman problem. Free software for solving Tsp. Popular Culture, Traveling Salesman, by director Timothy Lanswan, is the story of four mathematicians hired by the U.S. government to solve the most elusive problem in computer science history, P versus NP. See also, Canadian Traveler Problem, Route Inspection Problem, Set Tsp Problem, 7 Bridges of Car Paragraph Nigsburg, Traveling Tourist Problem, Tube Challenge, Vehicle Routing Problem, Notes. References. Further reading, Edelman, Leonard. Molecular Computation of Solutions to Combinatorial Problems, Science 266, 1021 Bibcode, 1994 Sci. 266.1021a, doi, 10.1126/Science 7973651, PMIDA 7973651 Aurora, S. Polynomial time approximation schemes for Euclidean traveling salesman and other geometric problems, Journal of the ACM 45, 753 doi, 10.1145/290,179.290180a. Babin, Gilbert. Danielt, Star Copyright Faney. Laporte, Gilbert. Improvements to the Opt Heuristic for the Symmetric Traveling Salesman Problem, KSDU GERAD, G 2005-02, Montreal, Group for Research and Decision Analyzer. Cook, William, In Pursuit of the Traveling Salesman, Mathematics at the Limits of Computation, Princeton University Press, ISBN A978-0-691-15270-7A. Cook, William. Espinoza, Daniel. Goyculier, Marcos, Computing with Domino Parity Inequalities for the Tsp, in Forms Journal on Computing 19, 356 365, doi, 10.1287/IJOC 1060.0204a. Corman, Th. Lesserson, C.E. Revest, R.L. Stein, C. 35.2 The Traveling Salesman Problem, Introduction to Algorithms, MIT Press and McGraw-Hill, PPA 1027 Euro 1033, ISBN A0-262-03293-7A. Danzig, G.B. Fulkerson, R. Johnson, S.M., Solution of a Large-Scale Traveling Salesman Problem, Operations Research 2, 393 Euro 410, doi, 10.1287/OPA. 2.4.393, JSTORA 166695A. Gary, M.R. Johnson, D.S., A2.3 ND22 Euro 24, Computers and Intractability, A Guide to the Theory of NP Completeness, W. H. Freeman, PPA 211 Euro 212, ISBN A0-7167-1045-5A. Goldberg, D.E., Genetic Algorithms in Search, Optimization and Machine Learning, Reading, Addison Wesley, Bibcode, 1989 Gasobook, G. ISBN A0-201-15767-5A. Gutin, G. Yo, A. Zvrovich, A. Traveling Salesman Should Not Be Greedy, Domination Analysis of Greedy-Type Heuristics for the Teaspoon, Discrete Applied Mathematics 117, 81 Euro 86, doi, 10.1016 per second 0166-218x, 01, 00195-0A. Gutin, G. Punnan, A.P., The Traveling Salesman Problem and Its Variations, Springer, ISBN A0-387-44459-9A. Johnson, D.S. McGeorge, L.A., The Traveling Salesman Problem, A Case Study in Local Optimization, in Arts, E.H.L. Lenstra, J.K., Local Search in Combinatorial Optimization, John Wiley & Sons Limited, PPA 215 Euro 310A. Lawler, E.L. Lenstra, J.K. Renocan, A.H.G. Schmoes, D.B., The Traveling Salesman Problem, A Guided Tour of Combinatorial Optimization, John Wiley & Sons, ISBN A0-471-90413-9A. McGregor, J.N. Ormerod, T. Human Performance on the Traveling Salesman Problem, Perception and Psychophysics 58, 527 Euro 539, doi, 10.3758/BF03213088A. Mitchell, J.S.B., Guillotine Subdivisions Approximate Polygonal Subdivisions, A Simple Polynomial Time Approximation Scheme for Geometric Teaspoon, KMST, and Related Problems, Siam Journal on Computing 28, 1298 Euro 1309, doi, 10.1137 per second 00975397963097664A. Rao, S. Smith, W. Approximating Geometrical Graphs via Spanners and Banyans, Proc 30th Annual ACM Symposium on Theory of Computing, PPA 540 Euro 550A. Rosenkranz, Daniel J. Stearns, Richard E. Lewis, Philip M., 2, An Analysis of Several Heuristics for the Traveling Salesman Problem, Siam Journal on Computing 6, 563 Euro 581, doi, 10.1137/0206041A. Vickers, D. Butavicius, M. Lee, M. Medvedev, A. Human Performance on Visually Presented Traveling Salesman Problems, Psychological Research 65, 34 Euro 45, doi, 10.1007 per second 00426000031, PMIDA 11505612A. Walshaw, Chris, A multi-level approach to the traveling salesman problem, CMS Presser. Walshaw, Chris, A multi-level Lin-Kernighan-Hellscorn algorithm for the traveling salesman problem, CMS Presser. External links, Traveling Salesman Problem at University of Waterloo, TSP-LIB at the University of Heidelberg, Traveling Salesman Problem by John McLoone at the Wolfram Demonstrations Project, Source Code Library for the Traveling Salesman Problem, T-spoon solvers in for symmetric and asymmetric TSPs. Implements various insertion, nearest neighbor and 2 Opt heuristics and an interface to Concord and chained Lin-Kernighan heuristics. T-spoon solver with Bing Maps solves T-spoon in TSP-TW, Traveling Salesman movie, Traveling Salesman in Python and linear optimization. IBM developer works with source code by Noah Gift.